3.3 volt ECL Programmable Delay Chip MC100EP196 by ON Semiconductor. Welcome to the training module on MC100EP196. Our training outline consists of features, emitter-coupled logic, ECL clock distribution technique, logic diagram and duty cycle skew, and multi-channel deskewing. The MC100EP196 is a programmable delay chip desired primarily for clock deskewing and timing adjustments. Programmably, it provides variable delay of differential ECL input signals. The EP196 has similar architecture to the EP195, with the added feature of further tunability in delay using the FTUNE pin. The FTUNE input takes an analog voltage from VCC to VEE to fine-tune the output delay from 0 to 60 picoseconds. ECL, also known as emitter-coupled logic, derives its name from the differential amplifier configuration, in which one side of the differential amplifier consists of multiple input bipolar transistors with their emitters tied together. An input bias on the opposite side of the differential amplifier causes the amplifier to operate continuously in the active mode. Consequently, ECL consumes a relatively substantial amount of power in both states, but also results in the fastest switching speeds of all logic families. If all inputs are at 1.6 volts, the input transistors will be all off, and only the internal differential transistor will conduct current. In this slide, we offer information about logic diagram of this device. The delay selection consists of a programmable matrix of gates and multiplexers as shown in the logic diagram. The delay increment of the EP196 has a digitally selectable resolution of about 10 picoseconds and a net range of about 10.2 nanoseconds. The required delay is selectable by 10 data select inputs, all D9 through 0 values, and controlled by the LEN pin. A low level on the LEN pin allows a transparent load mode of real-time delay values by D9 through 0. A low to high transition on LEN will lock and hold current values present against any subsequent changes in D10 through 0. The approximate delay values for varying tap numbers correlating to D0 through D9. In this slide, we discuss about the emitter-coupled logic clock distribution techniques. Emitter-coupled logic clock distribution illustrates a two-level clock distribution tree which produces 9 differential emitter-coupled logic clocks on 6 different cards. The emitter-coupled logic in picoseconds of the E211 device gives the flexibility of disabling each of the cards individually. An emitter-coupled logic clock driver will be significantly faster than a TTL or CMOS equivalent function. Therefore, to deskew the emitter-coupled logic and TTL signals, a delay needs to be added to the input of the emitter-coupled logic device. The value of the delay element would be a best guess estimate of the differences in the two propagation delays. This slide offers information and capability of fine-tune feature present in this device. The analog FTUNE pin on the EP196 device is intended to add more delay in a tunable gate. This requirement is easily achieved because a 60 picosecond additional delay can be obtained over the entire FTUNE voltage range. This extra analog range ensures that the FTUNE pin will be capable, even under worst-case conditions, of covering a digital resolution. There are numerous voltage ranges which can be used to cover a given delay range. Users are given the flexibility to determine which one best fits their designs. In this slide, we introduce cascading multiple devices. To increase the programmable range of the EP196, internal cascade circuitry has been included. This circuitry allows the cascading of multiple EP196s without the need for any external gating. Furthermore, this capability requires only one more address line per added E196. Obviously, cascading multiple programmable delay chips will result in a large programmable range. However, this increase is at the expense of a longer minimum delay. Clock skew. The difference in time between simultaneous clock transitions within a system is a major component of the constraints which form the upper bound for the system clock frequency. The skew introduced by logic devices can be divided into three parts: duty cycle skew, output-to-output skew, and part-to-part skew. ECL logic technologies offer a number of advantages for reducing system clock skew over the alternative CMOS and TTL technologies. ECL devices provide superior performance in all three areas of skew over their TTL or CMOS competitors. The most practical application for EP196 is in multiple channel delay matching. Slight differences in impedance and cable lengths can create large timing skews within a high-speed system. To deskew multiple signal channels, each channel can be sent through each EP196. One signal channel can be used as a reference, and the other EP196s can be used to adjust the delay to eliminate the timing skews. Nearly any high-speed system can be fine-tuned to reduce the skew to extremely tight tolerances using the available FTUNE pin.